Hello guys, my name is James, and I've been asked to explain how Tesla coils work. So I've compiled a few videos here. Some of them are mine, some of them are not. So
We'll see how a Tesla coil works. Before talking about how and why a Tesla coil is capable of generating those gigantic electric arcs, we have to understand what Nikola Tesla's objective and logic was when developing this device. Could apply current to a coil to generate a magnetic field, and in turn use this magnetic field to induce a current in a nearby coil, with which we would be transmitting power wirelessly. The problem with this idea is that magnetic fields lose their strength quickly as we move away from the source, and therefore, when separating the two coils, the energy transmission becomes more and more inefficient. Now let's see how the Tesla coil overcomes this limitation, taking this concept to the extreme. The logic is the same: to make an alternating current go through a coil, but with extremely high voltage and a specific frequency to be able to transmit energy over greater distances. To achieve this goal, there are mainly two concepts that we must understand. The first is the voltage rise through a transformer, which in simple terms is made up of two coils. A primary winding, which is connected to a current source and generates a magnetic flux, and a secondary winding, which converts again that magnetic flux in a current. But the interesting thing is that if the number of turns on the secondary winding is greater than the number of turns in the primary winding, an output voltage larger than the input is generated. A resonant circuit is made up of an inductor and capacitor. A resonant circuit has two great benefits. The first one is that even when they can't hold energy indefinitely, they can do it for a certain period of time, although losing strength in each cycle, something similar to what would happen in a pendulum, which just by pushing it once, is able to keep oscillating at a regular frequency. And also, like a pendulum, if we push it periodically at the exact moment, we can amplify the end result, even though we are only applying the same amount of force that we had initially used. The second benefit of resonant circuits is linked to the fact that they have their own frequency at which they oscillate. Taking this into account, the inductor of the circuit will generate an electromagnetic field whose oscillation is going to be equal to said frequency, which, let's remember, is constant. And did you know that another object does something similar? A tuning fork, which when hit, generates a specific frequency. And I mention it because you surely have heard of the following experiment, in which, when putting two tuning forks with the same frequency of vibration and hitting just one of them, eventually the second tuning fork will start to vibrate because the pressure changes traveling through the air from the first tuning fork will move the second one just at the exact moment so that their movement is amplified. Exactly as in the case of the pendulum. So thanks to this behavior, if we position two resonant circuits, but only the first one is active, eventually electromagnetic waves generated by its inductor will begin to induce and amplify a current in the inductor of the second resonant circuit, enabling power transmission wirelessly over much greater distances. Having taken all of this out of the way, now we are able to go back to our Tesla coil to see how it works.
yeah, so the main part of a Tesla coil is there's two resonant circuits. I like to call them tank circuits. They have a bunch of names though. But the tank circuit only consists of two components. There's an inductor, or a coil of wire, and then a capacitor. And there's two of these circuits. There is a driven one, which we call the primary, and there is an induced one, which is the secondary. This is the secondary, and this is the primary. So I want to give you guys a closer look at my spark gap. So the one shown in the video is stationary spark gap. Well, this one here is a rotary spark gap. So you can see it spins, and this is an angle grinder. It spins it when it's plugged in. The main reason for this is the voltage that I drive my Tesla coil at is very high, even compared to other Tesla coils. The voltage that I drive this at is around 24,000 volts. And so what the rotary spark gap allows me to do, actually shut off the arc. It will act as a stationary spark gap, but the thing is, the voltage that I'm using is so high that the arc doesn't really turn off. It's continuously flowing. It never breaks. And really what the spark gap is, or what you want it to be, is a switch. You want it to be able to turn on and off the current flow. When there is no electrode here and there's just plastic, it will forcefully open the circuit and break the arc. Once the electrode comes by, arc will form. So I actually have to correct a small mistake that I made while explaining this. So when the spark gap closes and shorts, it allows current flow through the inductor, the primary inductor, and then when the spark gap opens, the magnetic field will collapse, and that will push current through the capacitor bank, charging it, and then it will resonate like that as a typical LC tank circuit does. And the changing magnetic field induces a EMF on the other coil. But the tank circuit, the secondary tank circuit, it's easy to see the inductor, but it's not as obvious where the capacitor is. You have to imagine a capacitor in very basic terms, where a capacitor is two conducting plates separated by an insulator. In this case, the insulator is air, and this metal donut, called a toroid, makes up one plate of the capacitor, and the other plate of the capacitor is actually the dirt, the ground, earth. So there's a capacitance between this and earth. That capacitance that this toroid forms with the earth, in combination with the coil's inductance, form a tank circuit, because all you need for a tank circuit is an inductor and a capacitor. The secondary tank circuit is said to have a natural resonant frequency because it's kind of hard to change it. So generally it's easiest to make your secondary tank first and then design your primary tank around that. So now I want to talk about actually tuning the Tesla coil, and what I have for that purpose is this tool right here. It has a big dial in the front, and these numbers are kilohertz, so 1000 hertz. So in an ideal scenario, what you actually would like to use is a signal generator and an oscilloscope, but those are tools that not everybody has. And this circuit is very simple, and it does work. So if you don't have those things, you can easily use this circuit. Now, I actually did not make this circuit myself. It was given to me by another Tesla coiler. But the schematic is very simple. You can see there's only a handful of passives here, maybe one active component, potentiometer, some LEDs, and some screw banana terminals. So I actually forgot to mention what I'm doing specifically in this next clip, and that is determining the natural resonant frequency of the secondary tank circuit. The way that you use this device is you have to connect it between an earth connection and the bottom connection of the Tesla coil. So first thing I'm going to do, I want to say something before I get started, by the way. If you are ever working with a Tesla coil, when you're grounding it, do not ground it to the same ground that your electric box uses, because if you do that, you're going to send transient pulses down your neutral line, and if you have sensitive electronics plugged in, it's probably going to break them. So you need to make your own ground, and that's what this is here. This is a spike made of metal. I have a wire connected to it up here and a connection up here. This is my own ground, not connected. It is connected to the same ground as the electrical panel, but I'm not using, it shouldn't send transients to anything connected to that because I'm not using the ground spike for the main ground. So I'm going to hammer this in. There we go. Now I have a solid ground connection. Okay, so after a small technical difficulty, I have the coil here in a glass jar just to prevent it from falling over. This alligator clip is connected down at the bottom. This black clip, it's hard to see, but it's connected to the stake in the ground. And I will plug the jack in to the tool. Scroll all the way to 0 and flip it on. And so now we're ready to find the resonant frequency on this Tesla coil. So I'll just sweep the frequencies here. And the brightest light is where the resonant frequency is. So it looks like our brightest light is right here. Alright, we'll just take it inside and see what that is. And there you go, you can see that the resonant frequency of the secondary tank is right before 300 kilohertz. So there you go. Now, so we can't change the resonant frequency on the secondary tank, but we can on the primary tank. I'll show you how. And so we must tune the primary to match the secondary. And now we know that the secondary is tuned right there at that first red line. That was probably my marking from several years ago. So now we're going to discuss how to tune the primary tank circuit. And to do so, I'm going to show some schematics that I've drawn of it. So first, I'm going to show you this unlabeled one. You can see on the left there's a high voltage AC source where power comes in, and it goes through, and the spark gap is connected there. And then on one side there is the primary capacitor, and that goes straight into the primary inductor. Then on the other side, there it goes straight to the primary inductor, but you can see there is an adjustable tap. That's what that means. And so where we are going to place the meter is going to be across the capacitor itself. Okay, so in order to test the primary resonant frequency, it's a little bit more complicated, but it's still not that bad. So first, what you want to do with the leads of the tester is take them and connect them at either end of the capacitor bank that you're using for the Tesla coil. You also want to short the spark gap out with a jumper wire like this, and then have the tap freely adjustable. And so first what you do is, this is the other end of the tap. So right now, since the tap is not connected, the whole circuit is open. And so I'm going to close it, and I'm going to pick a random test spot, and I'm going to pick this spot right here, which this is basically just a guess. We turn the tester on, and the way that we find the frequency at this, so we're changing the tap point to change the frequency of the primary tank circuit. So the way we find the frequency at this tapping point is by sweeping it, and you have to find where the LEDs are the dimmest. So they don't really get super dim, but if you look carefully, if we sweep it really fast, you can see that they go dim for a second. And it looks like that dim spot is right there. So I need to be at this first red mark in order to be in tune with my secondary. So I'm a little bit off. So I'll readjust the tap and test again. The spot that I'm currently using is this spot right here. So let's see what that frequency is. To me, this looks like the dimmest spot. You can see that this is actually 250. So it's a little bit off from the red line. Yeah, that's how you find the resonant frequency of the primary and the secondary. So I actually made a mistake when I was filming this. The reason that the primary and the secondary doesn't align, even though that's the tap I'm using and that tap works, because when the Tesla coil is actually making the sparks that it does, those add to the surface area of the plate of the capacitor, the toroid. And so increases the capacitance and decreases the resonant frequency. And so when you're tuning this yourself, I forgot to do this, but you need to consider the streamers and add them to the toroid while you're tuning as a bit of wire coming off um, in order to tune it effectively. Okay guys, that's pretty much all I had to say about tuning a Tesla coil, basics of a Tesla coil. There's one more thing I want to do before the end of the video though, and I want to show you guys this thing in operation because it's pretty cool. You learn a lot about Tesla coils, so I'm going to set this thing up, I'm going to fire it up, and we're going to see some sparks fly. So in order to control the voltage that goes to the transformer, I'm going to use this device right here, which is called an auto transformer, a Variac. The only thing it does is it takes the 120 from the wall and you're able to change it from 0 all the way up to full 120. So this right here is my favorite part of the Tesla coil. This is the main transformer. Okay, so Tesla coil's ready to go. I'm going to turn the angle grinder on, turn the lights out, then energize the transformer. Also, I'm wearing these headphones. I know it's not the best, but I'm wearing them for hearing protection because it can get pretty loud. I'm going to move the ladder slightly farther away. Let's try again. Yeah, I don't think it'll make that one. Let's move the ladder even further away. I really didn't think I was going to make that jump, right? Alright, I don't think it's going to make this jump. Like, holy guacamole. there's the breaker. Alright, I think that's it, guys. I hope you learned something, and I hope you enjoyed my Tesla coil.